approach to implementing EV infrastructure. My name is Sean O'Rourke. I'm a Vice President and Director of Electrical Engineering with WSP. I've been with WSP now for 21 years, worked on a variety of different projects across the country. In addition to my work at WSP, I also sit on the board of directors with CMA New England. And then also, within my town, I volunteer as a chair of my local school building committee. So basically today, what I want to do is run through some of the topics regarding electric vehicle charging. And with this, I just want to start out with some of the basics just for folks. So typically with electric vehicle charging, what you see out there are basically what we call 3 levels of charging: level 1, level 2, and level 3. So level 1 are typically just receptacles that are located adjacent to the vehicle. It requires you to bring your own cord to plug in and bridge the vehicle to the grid. Level 2 and level 3 are kind of dedicated infrastructure that you see with pedestals, cords attached to it that are used. So specifically with level 2, which is the most common deployments that you see, there's what are referred to as like level 2 slow, which are slower ones or lower wattage, and then other ones that go into a 3-phase system with higher wattage. The main thing to keep in mind is, with each of these levels, as you increase them, the electrical impact on your system gets more. But one of the other ones that you have to account for too is also dwell time. So if you have a short dwell time that, for our charging or for your passengers, you want to look at a faster charger for that to basically address some of their needs for that. However, if you have something with a longer dwell time, the need for higher charging typically isn't required. The other one to keep in mind as you're walking through these, and I found it myself when I bought my Tesla, is the charge connectors on every car are not the same. So typically on the far right, what you see is the Tesla connector or NACS. But then other vehicles have other charge connectors that are there. And typically what you would see for them is the CCS1 and the CHAdeMO, which is there, I think, for the Nissan Leaf. And then depending if it's a level 3 or level 2 charger, the equipment comes equipped with different plug configurations. So there's sometimes needs for adapters to bridge that. So as you're planning a lot of your electric vehicle infrastructure, there are terminologies that get thrown around a lot. And the 3 of them, what I show here, I want to describe a little bit for you. There's what's called EV capable, which is basically just upgrading your panels to be able to accept future electric vehicle infrastructure. There's EV ready, which takes that panel and then extends conduit wire out to a receptacle located at the vehicle. And again, bumping up your electrical infrastructure to accept that. And then finally, the typical one, which we have, which is called EV installed, which is a full system that would have the full charging conduit wire and the panel, all the infrastructure built in. So one of the things that has come to light with me is, as you're looking at some of these, depending if it's EV ready, EV capable, bumping up that electrical system to accommodate that future deployment. When you're doing that, National Electric Code for electric vehicle infrastructure requires all electric vehicle infrastructure to be sized as a continuous load. So essentially what that means is you have to assume that all chargers are charging it at 100% all the time. And that causes a problem as you're sizing your electrical system, because it causes it to get very large for some of the larger deployments. If you have a what's called a charge management system, which is one of the exceptions they give you there, that's a way that you can implement it to throttle the overall connected load to some value that you have within your system. So for example, if you only had, say, 500 kilowatts available in your system that you could dedicate to EV charging, you could put in, 1 megawatt of charging or 1,000 kilowatts, and then throttle that down or clip it to only 500 kW. One of the other things we're doing with a lot of our deployments is we're segregating electric vehicle charging onto its own meter. And the reason we're doing this is kind of a backwards way of looking at that later on. So in future years, when you go to deploy, you can use a separate portion of the code, section 220.87, that allows you to take meter data from historical figures and apply it to that calculation. So it's a kind of a backdoor way of being able to expand your electric vehicle infrastructure by using meter data that you have there. Now, a lot of the deployments that come out are either mandates or policies from state agencies or authorities having jurisdiction for some of the departments that we work with. So, as we've looked through these and worked on a couple projects throughout the country, we looked at New York State, and actually City of Boston, where I actually live right now, has mandates for all their projects that are going out. City of Boston was kind of unique. And one of the things that we looked at there is they give a point chart that's there. So they look at essentially level 1 and level 2 chargers as equivalents. So the projects have a certain point threshold they have to hit. So assuming it's, say, 48 points that they would need to hit, you'd have to put in 48 level 1 or level 2 chargers, the level 2 slow ones. But as you increase it, you go to a level 2 fast charger or 3-phase one, you would only need 6. And if you go to a level 3 DC fast charger, you would only need to install 2 of them as opposed to 48 level 1. So essentially what they do is, in this section of this code or mandate that they had, it acknowledges that having a DC fast charging, you can flip cars quicker and essentially address more cars with less electrical infrastructure. So was kind of a premise when we were looking through some of our larger projects. So when we look at EV charging, just taking examples, for you guys to look at. So here's a project of a typical parking lot where we have a certain amount of dictated EV installed, call it 12.5%. For doing that, to have EV installed for 12.5% or 10 spots, it would require essentially a 150 amp panel. Now, the EV ready portion of that, theoretically, this client wants 40% EV ready. Again, we have to size our infrastructure to accommodate that future growth that's there. So essentially, our 150 amp panel now grows to a 600 amp panel, which could be somewhat onerous for some clients. So this is a typical parking stall layout that we look at. Oops, go back one. Sorry about that. But for some of the bigger projects that we work on, and this is LaGuardia's parking garage that I did about 12 years ago, and I just used this as an example. This wasn't dictated at the time, but this garage had over 3,000 spots. And typically we're hearing some numbers on different projects throughout the country that they want, say 5% EV installed and 10% EV ready. So on these larger projects, what it does now is start creating larger and larger amounts of capacity that we have to build in. So for example, for EV installed, we'd have about, at 5%, we'd have about 0.5 megawatt of charging. The other EV ready would require another megawatt of charging. So in all, it's about 1.5 megawatts of power just for EV charging in these larger facilities. And typically on these are the ones that we'd be looking at a charge management system to kind of pull that down. But what happens is when we start looking at the number of spots and the amount of infrastructure, call it pipe and wire, that has to go into all these spots, it starts getting the cost of that and start getting pretty impactful as you're looking at an overall project. The other thing that comes up is, or other considerations you have to take is, those spots are all going to get striped and they're dedicated for electric vehicle charging. Sometimes what you see is what's shown here is ICE parking or internal combustion engines parking in EV spots, which causes some headaches. Striping, signage, stuff like that are all things that you need to consider as you're looking at these on some of your larger projects. One of the other ones that kind of goes unnoticed is ADA access. For your handicap spots, you still have to provide EV charging, but how you locate that charger is specifically important. And in all my slides, I put the references to the websites at the bottom. So with these, placement of the electric vehicle infrastructure, access to them from wheelchairs or accessible needs are there. For example, the picture on the bottom shows the charging behind the curb. So I just offer this for everybody's input as they're looking at it. One thing to note too is as I'm going through this presentation, if you have questions, please just enter them in the chat and we'll address this at the very end of our presentation. So as I mentioned previously, this is a typical distribution system for a facility, either a building, parking garage, or what. With these, as I mentioned, for the larger deployments of what we're doing for electric vehicle infrastructure, we're trying to divorce it off the existing overall electrical system and segment it on its own and separately meter it. And again, we do that mainly to capture that true electric vehicle charging data. The reason the code currently requires you to carry it as a continuous load is they don't have data for it right now, so they can't apply demand factors on there. As an example, an electric dryer, if you're doing a very large apartment building or something like that, as you start installing more of the dryers, they allow you to use the demand factor to reduce that calculation. With electric, and it's mainly because they had historical data on that stuff, whereas electric vehicle charging, they didn't. So, a real life example, when I look at this, as I mentioned, I use my car. And just to be clear, my car is not pink. My daughter likes to play with the application on there to change the color of it. But on a recent trip out of Logan, I plugged in my car and had a 41% state of charge or remaining battery that was on there, so it wasn't at zero. I plugged into a level 2 charger, and that level 2 charger told me in 8 hours, 20 minutes, I'd be at 80% of my charge. My trip to Detroit was 3 days, but essentially my car would be charged within 8 hours. So I'm basically occupying a spot for 2+ days that nobody else is able to use it. So one of the things that comes into account or you have to look at for this is charging is not a constant. So you don't plug in and it draws the same amount of power throughout the entire time it's charging. It varies, and it varies by that state of charge. So what you see here is a graph that looks at, typically your max power is as you're charging up from 0 to 20 to 40%. And then that's typically your quickest charge going, at a 40% differential. But as you hit a certain amount on your battery, the charge management system that's internal to your car that protects the battery, what it does is it takes that charge and throttles it down to a certain point. So on Teslas, they actually ask you just to charge to 80% because anything over that could be detrimental to the battery. And the way they protect that is by throttling that charge that you're able to draw down further. And what that does is, if anybody has a Tesla, that's why it takes so long to charge from 80 to 100%. It basically takes just as long as getting up to 80%. So this website that I found out of Spec Studios, they've looked at different models. And what you see here, it looks like chaos of a lot of lines. But what they did is they graphed the charge profile of all the different vehicles that are on here. So if you're looking for data or stuff like that, feel free to utilize the site. It's very helpful. What I've done is just looked at a couple different kind of common cars that we had there: the Tesla Model Y, the Model 3, Hyundai's Ioniq, and the Kia. And as you can see with each of these, the charge profiles on them are a little bit different. The Tesla Model 3 ramps up, follows that grid, follows that slope coming down. Kia is kind of flat. The Model Y that's here, again, flat but tails off. And then the Hyundai Ioniq had a different one. The point of this is that not all charging is consistent, so it's not all flat. So one of the things we look at when we're doing this too is, on the infrastructure for parking lots or parking garages is, the request for higher amounts of charging comes into play. But one of the things to keep in mind is there's the National Vehicle infrastructure NEVI bills that are out there that are creating roadside charging. So the need to charge at parking facilities will probably reduce over the next coming years as NEVI becomes more prevalent, and they create what are called alternative fuel corridors, or AFCs, through major interstates. So the innovation that I wanted to talk about today, I had a project that we're working on for a client. It was a parking garage of about 4,000 spaces. The sustainability consultants for the authority that I was working with requested 25% of the spaces, or 1,000 of them, be EV installed, and the remaining 75% be EV ready. So basically equip the entire garage for that. As I was mentioning previously, that type of electrical infrastructure we'd have to put in to accommodate that request was astronomical. It was basically cost prohibitive to do it. So what we did is we took the other facilities at this airport, looked at their exit data from other garages that they had there to kind of get an idea of when their peaks were happening. And then basically for that, we looked at how many registered vehicles there are in the state of Massachusetts and compared that exit data to the percentage that we would assume are electric, and then looked and said, this is how many peak electric vehicles will be exiting our facility that we're using, basically scaled all the data. And when we looked at it, we came up to about 9 cars maximum exiting that would need to charge. So what we did is we took part of the facility that we had, and instead of equipping the entire parking garage with charging, we created what was called a hub. And right prior to the exit plaza, we put a hub in here that will have level 3 charging. That level 3 charging will allow passengers to charge really quick, top off, and return back, to their home where they typically have charging built in. These are examples of other charging hubs that are around right now. Mercedes-Benz down in Sandy Springs, Georgia. London Gatwick at the airport has an EV charging hub, and all of these are basically showing a new trend of kind of transitioning away from level 2 charging throughout large facilities and more to concentrated level 3 charging to service more customers that are there. And with that, I'll open it up to the questions that I believe are getting populated in the chat. So just give me 1 second, I'll take a look for them.
Shin, thank you so much for this insightful presentation. Yeah, actually we have a few questions in the chat, so we can start with this one from Martin. So he asked, where did the level 1, 2, and 3 definitions for the charging speeds come from? Are these universal terms or a grouping by WSP?
No, so they're typically universal terms. I don't think there's a strict classification for them, but typically there are thresholds based on how much power they can transfer through. So, and the other one that comes in is the voltage ratings that they deal with. So the typical DC fast charging, the level 3s, typically operate at 480 volts, 3-phase, and it's just an easier way to push more power. The level 2s are typically 208 volt, either single phase or 3-phase, and the level 1s are typically 120 volts, single phase. I hope that helps.
Sure, thank you. Next one is, why are the SOC graphs different for different vehicles? Is this because of the difference in battery chemistry for different manufacturers? Sorry.
Yeah, no problem. So I don't believe it's based on battery chemistry. Each model that was presented there basically has different charge management software that operates it, and probably different algorithms for when they want to throttle charges. As I showed on the one with Tesla and I think it was the Kia one that was flat. It's different engineering technologies that each company is using. And the point of that slide was just to show that as cars plug in, they're not pulling constant load over long periods of time.
Great, thank you. Next one says, Davin says, hello, great presentation. We are seeing more EV design here in Canada. Do you have recommendations for charge management systems that limit the demand load on existing systems?
Yeah, it's a good question. And just for the record, my father is originally from Canada, Nova Scotia. So I appreciate you guys logging in. For the charge management systems, it typically breaks down to specific manufacturers. But if you look it up, there's different ways they do it. So if, for example, they sometimes have the software program to do first in, first out. So if you have a dual port one where a first car pulls in, that gets the majority of the charge, and it stays on the majority of the charge, even if a second one plugs in. And then as it finishes its charge and pulls out, the larger amount of power would then go to the next car. So that's basically, I think it's called first in, first out. There's different acronyms used for it. Then they have other ones that are essentially power share. So assume you have a 100 kW charger. One car pulls in, it gets all 100 kW. A second car pulls in, it would basically split it to 50-50. And sometimes you can spread it over multiple chargers so that 100 could get divided over, say, 4 cars down to 25. And then there's all different variations that they can do on that charge management system.
Okay, thank you. On that note, also, we have this question: have there been any EV charger designs meant to service multiple parking spots?
Yeah, so there's different technologies that are out there. So everything I was showing is basically fixed electric vehicle infrastructure. There are mobile solutions that people are looking at, or some authorities. Essentially what it is it's a battery bank on wheels that gets wheeled around to plug in to different vehicles. My concerns with that is you have to have some way for a passenger to tell you where they parked, that they need a charge, and when they arrive and when they're departing, so that you know when to bring or schedule the deployment of that mobile infrastructure. There are other type of ones that aren't mounted on the floor. They're mounted on the ceiling that basically come down and it frees up some of the floor, but that's not really much of the mobile stuff. It's still fixed.
Okay. Next one is, do customers pay for charging? What are the revenue opportunities?
Yeah, good question. So some of the facilities, or at least some of the ones I worked at, offer it initially complimentary, because some of the larger facilities I work with buy bulk power at a very discounted rate. So it's not a large financial impact to them, but for smaller customers, you can charge for it. And typically the way it's done is customers would come up, the station or the charging station has a cellular signal to it, and you would just use it almost like the wireless parking meters that are there. You'd swipe your credit card, and then it would basically charge you for the amount of power that you would draw. So whatever that total amount of power over however long you're charging for, it would charge your credit card. Some of these actually require third-party applications or apps that you'd have to download as part of them. But from a owner point of view, you can work with whoever you team with your infrastructure to kind of negotiate that.
Okay. There are questions about that. If an entire building is backed up by an emergency generator, how do you manage disabling the charger when on emergency power?
Yep. So if the entire, so I think the question, if I could read it correctly, could potentially be load shedding. So if you have an emergency power system and you lost power, and charging is not where you want that emergency power to go to, but you want it to go to other loads, you could set up a load shedding scheme, essentially by not to get too complicated, but shunt tripping a breaker basically when the call for the generator happens. So it essentially divorce the entire system off the emergency system. We see a lot more facilities now actually putting generators in to power the entire facility for backup power. But essentially, for the amount of charging, depending on how big it is, it might require you to put a very large generator in, which isn't required. So I think, at that point, you would just want to have a load shedding scheme to take that charging off, or use a charge management system when you go on a generator to clip it even probably further than what you initially had it set to.
Okay, so Jane says, yes, that answers the question. Thank you.
Yep.
Next one, where are things moving for street side telephone pole parking or other options for renters or people that do not have a parking garage or other options? Are we providing solutions like this?
Yeah, and that's typically when it gets down to the municipality level for deploying, call it curbside infrastructure that's there. I know I haven't done much with it with some of the cities I work on. More of the stuff I'm in is the transportation aspects of it, not the city end of it. I know there are plans to put them in, but it's mainly a lot of planning that's going on right now. I haven't seen much implementation of it.
Okay, we have 2 more minutes, a couple questions that we can take.
Sure.
Do you have any experience with owners' requirements for redundancy in charging infrastructure and how that was handled?
Yeah, so typically any of the electrical infrastructure that we put in, we build redundancy into it because nobody ever wants to be without power. So typically what we have is redundant utility feeds that come into a facility, and then from there it basically provides backup power, either a primary line or a redundant line, to your electric vehicle infrastructure. We typically do not put it onto a generator per that previous question, mainly because it would cause the generator infrastructure to be too large. In regards to like physical redundancy for the stations, as I showed in my presentation, like we calculated we only needed about 9 parking spots that we were doing for that previous project. For our deployment, we're actually putting in 20, and we do that again to basically build in, call it spare capacity or resiliency, that if a station, for example, was out for maintenance, there should be an additional station there that somebody could be able to access. So, it's always good to put a little bit extra in at the beginning.
Great. So one more and we can wrap up. How to balance the increased power requirements from emerging and disruptive technologies with EVNet?
Mm-hmm. Yeah, good question. So as you can see from this presentation, is like the more and more electric vehicle infrastructure you start putting in, based on today's code, it gets very disruptive just by the way you have to calculate it. But what I hope to do today was share some insights on how we might be able to game the system or play with it a little bit to allow you, if you have to put that in now, leverage it in the future by using that meter data that's there. There's also, at least at some of the airport facilities that I'm running into, there are other needs for charging infrastructure, whether it's airside electric vehicle infrastructure, or infrastructure for EV tolls, which are EV takeoff and landing vehicles that are way in the future for stuff like that. But if you build out this infrastructure now, even though you may not use it all for your vehicle infrastructure that's being done right now, there's definitely potential in the future to kind of leverage it.
Perfect, thank you, Sean. Well, just one last one that just came in. In terms of harmonics on EV charging loads, is some sort of harmonic mitigation required?
Yeah, good question. So anytime you're chopping an alternating current signal and basically turning it into DC, there's concerns of harmonics. IEEE, I think it's 419 is the standard, requires there's a minimal amount of harmonics that you can reflect back onto systems. I believe with all of the electric vehicle infrastructure that's there, there's harmonic requirements for them that they're not reflecting those back. And so, it's similar to the inverters that you have for photovoltaic systems. There are specific requirements there. I don't know it totally off the top of my head, but that would be my anticipation for, the response for that if it came up.
Sure, perfect. Well, a couple people are asking if you can share a copy of the presentation. So if you want, we can work in a PDF version and I can share it with them.
Yeah, the links to everything are on the bottom right-hand corner, so allow them to kind of get to the websites. They might be able to do a deeper dive.
Sure, perfect. Thank you. And well, I think that's all the questions that we have. Thank you so much everyone for putting those on the chat. Thank you, Shen, for the session. You can wrap up.
Okay. Thank you very much. Have a great day.
Thank you.